All right, let's look at doing an example using integration by parts. So I have the formula up here. Remember u dv, that integral is uv minus the integral of v du. Let's look at this sort of quintessential integration by parts example, x e to the x. So the idea with integration by parts is, remember, you're thinking of this as a product. So those two things represent two pieces in your integral. And that's really the decision you have to make, is what makes sense here as my u and what makes sense as my dv. And I usually write it like that because I'm going to make a little table here, u du v dv. So part of this needs to be represented by u and part of it by dv. Now let's think about the logic. What's the new integral? The new integral is going to be v du, which it's going to be the derivative of what I put here, right? And the antiderivative of what I put here. So whatever I put as u should get simpler when differentiated. And whatever I put here as dv should not get more complicated when integrated. Think about x. If I put x as my u, its derivative is just, well, its differential is just 1 dx. It gets much simpler. If I put x here for dv, integrating makes it more complicated, 1/2 x squared. E to the x actually is good either way, right? The derivative of e to the x is e to the x, doesn't get any simpler. Antiderivative is e to the x, doesn't get any more complicated. So the fact that when I differentiate x, it gets easier, leads me to believe that that should be my u. And then the e to the x dx will be my differential dv. Now, I just fill in what my differential du is. Derivative of x is 1 dx. v is e to the x. Again, as I mentioned in the development, technically there'd be a plus c here, right? But there's still going to be an integral when we're done, right? We're not actually finishing, we're just replacing with a new one, so I'll leave the constant out. All right, so the formula tells us that it's u times v x e to the x minus the integral of v du, which is just e to the x dx. So we started with this integral, x e to the x, and now we have something that we do know, right? We know the antiderivative of e to the x from Calc 1. So we've reduced it down to something that we can do. Now we just do that integration. Antiderivative of e to the x is e to the x. And now, since we're all done integrating, now we'll bring in our constant of integration there, c. So you have to make a little bit of a decision here. What is u and what is dv? If you have this wrong, it'll be really obvious when you get here. You'll have an integral that looks much, much worse than the one you started with. In this case, if you had these reversed, this integral would be 1/2 x squared e to the x, which is the same as this, but a degree higher, so it's gotten more complicated. So if you just think a little bit about what you want, this is going to be v du. So you want v du to be something nicer than the original. And that should help you decide what your u is and what your dv is. Notice u and v are just names we use to keep track. That was an integral involving x. That's a function involving x, integral involving x. Answer involves x. We never switched variables. So unlike u sub, this is not a new variable ever. It's always the original variable. So there's no need on a definite integral to switch limits or anything like that. All right. Next time we'll look at the idea of using this repeatedly. You may apply integration by parts and get here and have something nicer, but still not nice enough. We might reduce things down a little bit, but if we did integration by parts again, we would get it even nicer and nicer until finally, after enough repeated applications, we'd get down to something that we know the antiderivative of. So we'll look at that next time.